Hello, Year 7. Today we're going to do about forces and what they are. When we go back to school, there'll be some sort of practical involved with this, but for today we're going to focus more on the drawing of the diagrams. Okay, so here is your intro to forces folder, and I'm on the PowerPoint right now. Later on, there'll be a picture. It will look like this. If it's hard for you to edit on the PowerPoint, here is the Word document for you to do the same. Now, start off with which of these words are forces. So pause the video, sorry, and I'll write down the ones that are forces. Okay. So, weight is a force. Friction is a force. Twist is a force. Push and pull are forces. Mass is not a force. Okay, mass is not a force. I specifically mentioned that one because mass and weight are related very closely. Your weight equals your mass. This is in kilograms. Okay, so your weight in newtons, which is a force, is your mass times the strength of gravity. And on this planet, the strength of gravity is 9.81. Okay, so what that means is for every kilogram of mass you have, you will feel a force of 9.81 newtons. Now, okay, pause the video if you'd like to read the lesson objectives, and then when you're ready, unpause it and continue. So, what is a force? A force is an action that can change the shape of an object or change an object's motion. So that is a very good definition. I'd like you to write that down, please. And once you've done that, think about what forces are acting on this duck. Okay, and I'd like you to, if you want to, you can draw a diagram to show and then come up with what forces you think. So this duck is stationary on a table. So hopefully we've got that the duck has a weight due to gravity. If you put gravity, I'll let you have that for now, but I prefer it if you said weight, okay, because weight is the force that you feel because of gravity. And because this duck is not falling through the table, it is sat on the table must be pushing it up. And that we call that the reaction force. Now notice that the arrows, okay, these two arrows which represent the forces, they represent the size of the force. So the size of the arrow represents the size of the force, and the direction of the arrow represents the direction of the force. Because this arrow and this arrow are equal in size, but they are opposite in direction, what happens is the forces cancel each other out. Okay? We say that the forces are balanced. If the forces are balanced, this duck will be in equilibrium. And that is a very important word. If you find that all the forces are balanced on an object, it is in equilibrium. And in this case, the duck will be stationary. Now, what happens if we remove the table? Think about the forces that are in play right now, and what happens if we remove that table? Well, there is no longer the reaction from the table onto the duck. So the table is no longer pushing the duck up. So what will happen to this duck? Well, these forces are now unbalanced. We actually say that there is a resultant force. If the forces are not balanced, there must be a resultant force that acts in a specific direction. In this case, it's easy because there's only one force. So this has to be the resultant. Now, because the only force is pointing downwards, that means that this duck will start to accelerate downwards. And remember, accelerate means to speed up. Okay. So, the duck falls. Okay. Another thing. We say that forces the opposite forces in the first diagram. There was the reaction force from the table and the weight force from the duck. We call them interaction pairs. So if you are sat on a chair right now, or lying on your bed, whatever you are lying on or sat on is pushing you up, and it's equal and opposite to the force that you are pushing down. If it wasn't equal and opposite, the chair would break because your force would be too big, or the chair would fling you off into the distance, which doesn't happen. Now, if an object has balanced forces, this is kind of difficult to think about until you get the hang of it. If an object has balanced forces, it will continue moving at the same speed. So let's look at the duck on the first slide, right? The duck on the table, it had a force going up and a force going down. They were balanced. Now that duck was not moving. Okay, it had a constant speed. And that constant speed was 0. Okay, so that duck is moving at 0 meters per second, and it will continue to move at 0 meters per second. For us, 0 meters per second is a special thing because we're not moving at all. Now let's say I had a car. Again, this is a car, and it's moving to the right with a drive force. So I'm going to call it a push. The engine is pushing the car forward, but the wind resistance is dragging the car back. If you've ever rode a bike and like stuck your hand up while you're riding your bike, you can feel the air pushing your hand back, or you can feel the air on your face pushing you back. So what happens is, just assume that I've drawn these arrows equal in size because they're a little bit wonky, and they are opposite in direction. Because they are equal and opposite, okay, they cancel each other out completely. Just like in this first one here. There is no resultant force. So this is an equilibrium. So let's say that this car is moving that way with 10 meters per second. Or 20 miles an hour. Okay, the number doesn't matter too much, but what happens is if this is an equilibrium, this car will continue to move in a straight line at that speed forever, until the forces change. So, right, we need to know that we measure the unit of force in newtons, and it's named after the person that first discovered forces, or first proposed equations for forces, I should say. We can measure a force directly using a Newton meter, or, like I showed you in the first slide, calculating the force as a weight using the mass. Now the next thing we're going to talk about is what types of forces are there. So, we've got non-contact forces, and these are the only 3 non-contact forces that you need to know about. If you come into contact with any other forces, they will be contact forces. So the 3 non-contact forces you've got are the electrostatic, you've rubbed your hair on a balloon, you've had a static shock before, okay? You rubbed your hair on a balloon and put it somewhere, you'll find that your hair sticks up or the balloon sticks to the wall. That is the electrostatic force. There is a magnetism. That is a non-contact force. And then this is gravity. That is a non-contact force. If gravity was a contact force, as soon as you jumped up from the floor, you would just fly off into space, okay? And because that doesn't happen, you know it's a non-contact. Now, I would like you to look at these forces. You can see, so I'd like you to look at this picture, and on the left hand side you can see that there is a list of different forces. So if you can find other forces, that's perfect, but here are some ideas for the names of forces. I'd like you to go and draw arrows and label a few forces on this diagram. You only have to do maybe 5. Don't go too crazy because there is loads of forces on this picture, just to get the right idea. Okay, for example, if I was going to do one, let's do this one here. Okay, pen. Like this dog, the dog here is pulling this cat's tail back. So this is a pull, because it's bit it, right? But the cat is still trying to run away. So the cat is trying to push away from the dog, right? So you get the idea. This person here is falling to the floor. He's got weight, but because he's not quite hit the floor yet, that is the only force that's acting on him until he hits the floor, and then he will be in equilibrium. Might hurt his head a little bit. Now, once you've done this, we've got one more task we need to do. So have a go at that, put some forces on, pause the video while you're doing it, and then when you're finished, you can unpause. Okay. The next thing I want you to do is draw some force diagrams, or we can call these, sometimes we call them force diagrams. I like the term free body diagrams. Okay, we're going to draw some diagrams. Force diagram or free body diagram. So you've got some situations here. You've got a box on a chair. You've got a boat that is just floating. You've got a person that has just jumped out of a plane. Excuse my handwriting. I'm going to read them out so you can understand what it is. You've got a car that is stopped or stationary. You've got a car moving at a constant speed, and you've got a car that is accelerating. So I'm going to get rid of these because they might get in the way. Now, so I'm going to do the box on the chair to start with. So to give you a hint on how to do this, I'll draw my chair. There's my chair. I'm going to do my box in, I'll do my box in blue. There's my box. I like to draw everything as a box or a circle because I'm a physicist and it makes life easier. So I'll actually do this one for you. I'm going to make my pen a little bit thinner. Okay. And I'm going to do the forces in green. So there is a force on this box that's pulling it downwards. That is called the weight. Now, because this box is on the chair and not falling to the floor, the chair must be pushing upwards, but the chair must have, so this is the reaction force, I should say. The reaction force, but look, I've tried to draw it as best as possible. These arrows are equal in size, but opposite in direction. So this chair is in equilibrium. Now, for the next diagram, the next 1, 2, 3, 4, 5 diagrams, I'd like to have a go. I'm going to give you a few seconds to try it. Then I'm going to draw the diagram without the forces on, just to give you a start point if that makes it a bit too difficult. Drawing the situation beforehand. Then, after that, I'd like you to pause it and try and do them all, and then I will go through and give you the answers. So I'm going to go through and draw just the situation to start with. Well, since it's a boat floating in water, let's make the water. Do the boat in pink. And my boat, actually, no, I'll actually make it look a bit like a boat. There you go, there's my boat floating in the water. Person just jumped out of a plane. Okay, there's my plane with a wing. That's actually not too bad. And my man is, there's my person. He's literally just jumped out, so he's not started moving yet. He does have a parachute on, so don't worry about his safety. So there's my person. I've got a car that is stopped, so I'm actually just going to draw my car on the floor. So here's the floor, and here's the floor. My car can be blue. There's my car. There's my car again, and there's my car. My car's got a white roof, so I'm not going to draw that. Now that I've drawn the situations, pause the video, have a go at the forces on each one. I've just given you a hint on what one of the forces might be, but try and have a go at the forces on each one. Once you've finished, unpause it, and we'll go through. Assuming that you've done that now and you'd like the answers, let's have a go. This boat that's floating here, well, the weight force, from now on I'm just going to label weight as a capital W. just so we don't have to write it every time. Now this boat is floating and it's not moving, so it has an equal and opposite force because the water is pushing it up. So boats float because water pushes them up. I don't know if you have noticed, but whenever you go swimming, if you've ever been swimming, you'll feel lighter when you are in water because the water pushes you up. It's called buoyancy. The force we call that is upthrust. Okay, now this person, he's just jumped out of a plane. Now I'm going to get rid of the plane because it's not necessary for the forces that we're going to feel. Okay, so I'm going to get rid of the plane. Plane's gone. He's just jumped out. Now he has his weight force going downwards. Now if he has just jumped out and he's not moving, that'll be the only force he's got. So he will accelerate. Okay? But if he has started to move, he will have a little bit of air resistance. I'm going to call that drag. Notice that this drag arrow is a lot smaller than the weight arrow, so this person will accelerate downwards. So a car that is stopped. So if it's stopped, it's got a weight. Notice that I try and draw the arrow from the middle of the box. For me, that makes it easier. Some people like to draw it from the edge of the box. Okay, I like it from the middle because then I can see where all of the points converge. And because this is not moving, the reaction force, I'm going to put a capital R for reaction, is equal in size but opposite in direction. So here now we've got a car moving at a constant speed. Well, it still has to have a weight. The car's got a weight. Doesn't matter if it's moving or not, it's got a weight. And because it's not falling through the road or flying off into the distance, the reaction force must be equal and opposite. But this car's moving at a constant speed. We know those two forces are equal and opposite, so I'm going to change colour to yellow. Well, what about the drive force? The car's driving. Okay, it's pushing itself, so I'm going to call that push. Now, because we are moving at a constant speed, we should know that this is an equilibrium. So that means that the drag force has to be equal and opposite. So in this one that we've just drawn there, the reaction and the weight are equal and opposite, and the drag and the push are equal and opposite. So this is an equilibrium too. Now let's do the car accelerating. Again, the car's not falling through the floor or flying off into the distance, so the weight and the reaction must be equal and opposite. But this car is accelerating. It has a push force. Okay. Now it has drag or air resistance. I like to call it drag because it's a general term. Drag can happen in water as well. Doesn't just have to be in air. So the drag is pulling it back, but the drag force is much smaller. Now that we've done all the forces, okay, I want you to go and tell me what's happening in each photo. So is it stationary? Okay. Is it moving but constant? So it's got a constant velocity. Or is it accelerating? Now, okay, so you've got three options. So pause it, have a little go through. Hopefully you got that this one is stationary. This one is stationary. This person here is accelerating. The car that is stopped is stationary. The car that's moving at a constant speed, well, we said it's moving at constant. And this car that's accelerating is accelerating. Now the last thing, I'd like to circle the ones that, the letters or the situation that's in equilibrium. So pause it, have a little go. Okay. Well, if anything is stationary or moving at a constant speed, it is an equilibrium. We've already said all the forces are balanced on this one and this one. The forces are not balanced in this one. Okay, so it's not in equilibrium. Now, the car that is stopped, this is in equilibrium. Notice all the forces are balanced. The car that's moving at a constant speed. Now, you have to look at this in two different sections. You see, these two are equal and opposite, so they are balanced. That one and that one is. These two here, the weight and the reaction, are equal and opposite. So that is in equilibrium. The acceleration one here, the reaction and the weight force are equal and opposite, but the drag and the push are not. They are opposite, but they are not equal. So this one is also not in equilibrium. Okay. That is the end of today's lesson. Hopefully you are a bit better at drawing free body diagrams. Hopefully you understand a bit more about forces. So take a photo of your work and then email it to me, please.